All right. So what do we have left? Before the final, although we aren't going to have individual tests, like for example, chapter 19, we're going to have an individual test. Chapter 20, we'll have an individual test. But for chapter 24 and 25, that'll probably be rolled into the final exam because of just the timing wise.
And the final is cumulative.
The final's cumulative, and so I got a question in the afternoon about, is it going to be heavily biased since 25 will be on the final and 24? Is it going to be like half 24 and half 24 and 25 and the other half the rest of the class? And it's not going to be like that. It's just going to be, there's going to be approximately 60 multiple choice questions for the final exam. Yeah, maybe more. And so that means between, let's say, 5 and 10 questions per chapter. That's what you can expect. And so maybe 10 questions from 25 or something, or 8 questions. You can't do too many questions. Since there are a lot of questions there, you don't have much time for each question. And if there's 60 questions and you take, 3 minutes a question, that's the entire 3 hours, right? And so you have to have less than 3 minutes. You have to have more like average 2 minutes per question. Then that's what I was thinking, about 2 minutes per question. But that's average. Some questions are very fast. Other questions require a little bit of calculation. It takes some more time.
Is it all in multiple choice?
No, it's not all multiple choice. So this is getting back to Omar's question about the chemical reactions homework. Now, the chemical reactions homework is worth 10 points, a half point each question. That's going to be due on the final. And the final exam is going to have some predicting products, where we did metathesis, redox acid base. In fact, we're going to be doing some predicting for redox in this chapter.
Will you put the sample final?
No, there's no sample final. The sample final, just go back, since it's mostly multiple choice, go back and look at your multiple choice.
It would be similar to that?
Mm-hmm. That would be similar to that.
What about the points for the quizzes? It's like we didn't do all the quizzes.
No, we didn't do all the quizzes. So there's going to be fewer points
No bonus
total.
points? No bonus points.
What do you mean by bonus points? Bonus assignments, extra credit? There are. Speaking of bonus, yes, there are bonus points on the final exam, actually.
Easy?
Easy? No.
Yeah, easy.
Nothing's easy. I don't know, because I think it's easy, but
No.
a lot of people think it's hard. And so I don't, somebody told me, actually one of my advisors always said, never ever say anything's easy, because nothing ever turns out to be easy. It always turns out to be much harder than what you think, even if it is easy. But I think that was the problem with the last time I taught this class. A lot of people bombed the final, and so I was thinking that maybe I told them it was easy. I shouldn't have told them it was easy. They didn't prepare.
Maybe it was just really hard. Yeah.
It's too long.
No, it's yeah. Well, some people finish early,
No, people they turn early to get a good score. But they doesn't know anything. They didn't know anything. They just turn it.
Yeah, that's true. That's true. Usually that happens a lot. No, the level is going to be. The way to think about this is, if you could only ask, let's say, 5 questions or 8 questions per chapter, what would you ask?
Definitions.
Yeah, the key definitions, stuff like that. Just.
Okay. But you'd also have calculations.
Yeah, right. What kind of calculations? If you had to choose 3 calculations, which ones do you think are the most important in the chapter? Know those for sure. And so, in a sense, It's that's a lot easier, I think, to study for than a final that has, let's say, 4 questions out of the whole semester. No, no note card. There's no note card, but you don't have to memorize the equations because I'm going to write all the equations and constants on the board, so you don't need a note card for it. Okay, other questions about the?
Oh yeah, what about the notebook? Are we have to turn anything in or?
Yeah, I want to take a look at your lab notebook. Yeah, at the end of the semester. I need to see if you've been writing observations and that kind of thing.
How many formal reports do we have this semester?
2.
Two. Synthesis and the
Synthesis and titration. I eliminated the kinetics one.
Thank you.
And for the acid strength, do we need to turn paper in or we can try like?
You just write your observations in your notebook. I'm going to check your notebook and I'll check it off then. Yeah, you aren't going to have to write a formal report for that or any kind of report. I'm just going to be looking at your observations in your notebook.
So is the points going to still stay the same?
No, the points are going to be a little different, and since the points are going to be a little different, I don't want the final exam to be more than 20% of your grade. So the final exam is going to just be whatever points we end up with at the end of the semester. I'll just make it worth 20% of the total. And so it's going to be, since you're going to lose some points, it'll be worth a little less than 200 points. Now there's bonus on the final, extra credit. Extra credit just, the final is going to be worth, you'll have a chance to earn extra points, like, I think like around 10% extra points. 10%. Yeah. And so this is why, when I said, if there's 10% extra points, then let's say, if you get a C on the final, that was really a D, so that's why I said that last year people did that. The extra credit isn't like one tough question. It's just a few extra multiple choice questions. That's all. But the multiple choice are going to be worth a lot more points, because they add up to 180.
We will have partial credit on multiple choice too, right?
What?
Partial credit on multiple choice.
No.
No, so just straightforward?
Yeah, except, let's see. Maybe 1 or 2, but most of the multiple choice are either get it right or wrong. Okay. No partial credit.
And no Scantron, right?
No, I need a Scantron. Bring a Scantron. One of the, what number it is? I forgot the number. 225 or something like that. The big one, yeah. Okay, other questions? This is good. Start preparing for the final. It's always good to start preparing for the final, just by reviewing your stuff. And as you go back and review, hopefully some of the earlier stuff is easy. But if not, you should make sure you get it cleared up before the final exam. Okay. I would start, the best way to study for the final is probably just reviewing the multiple choice questions initially and then go back through concepts, calculations, and homework last. Okay, is that it? Any other questions about anything? All right, now, when we build batteries, we usually write the anode on the left side and the cathode on the right side. That's just A. This is alphabetical, anode to cathode. This is a standard. It doesn't really matter because this left would be somebody else's right, but you just always build the batteries the same way. That way, it's you develop a habit. And it's,
It doesn't matter. It's just like
it doesn't matter, but just do it the same way. That way, you don't get mixed up. Because electrons flow which way? Well, electrons flow, let's not worry about minus to plus yet. Electrons flow from the anode to the cathode or the cathode to the anode? Anode to the cathode. So you want to build it this way because we want the electrons to flow left to right. Doesn't that make sense? What's pulling the electrons to the cathode? Well, it doesn't have to be a positive cation, you know. It could be a negative anion. How could a negative anion pull electrons towards itself? Is that even possible, a negative anion pulling electrons towards itself? Could a negative anion pull electrons towards itself? Negative and a negative, do they attract each other? No, and so is that impossible then? Huh? True or false? It's totally possible. You guys, why is it being pulled here to the cathode? Because what resides in the cathode? What is over here pulling the electrons? What do we call it? Do we call it the oxidizer or the reducer? The oxidizer resides here. So now can a negative anion pull it? Yeah, you know, one of the things El Camino does differently than, you know, when let's say, for example, at UCSB or UCLA, at Santa Barbara City College, the general chemistry, there's a pretty heavy emphasis on physics and not as much on chemistry. So a lot of people don't really get much chemical knowledge. You know, they could do some calculations like Bohr equation, this kind of stuff, lots of calculations, but they don't really have a good chemical knowledge when they finish general chemistry. And so that's one of the things that's done a little differently here. This is why on the final exam you're going to have that chemical reactions stuff. Because, yeah, are there oxidizers that actually have a net negative charge? Name one. Chromate, yeah. CrO4 2- is a powerful oxidizer. In fact, if you have chromate over here, chromate has a -2 charge and yet it pulls electrons. Why? This is the whole point of doing, you know, and actually you should know a whole bunch because permanganate, chromate, dichromate, a whole bunch on that chart, right? Negatively charged oxidizers. Normally oxidizers are positively charged, right? And so why is this, how could this be?
Because of the chromium.
Because of chromium, yeah. Because what we're doing is, this is the net charge. We got to look at it. Remember when we're doing Lewis acid-base reactions, looking at, yeah, this is a question, I don't know if I put it on the test, the last test, or not. I was going to put a question like this. You know, in the first step, did I talk about the first step of the acid-catalyzed formic acid decomposition? I guess I eliminated that. I originally had that question on there because I thought, okay, let's see what people are thinking. Can an acid attack an acid? Normally, no. You'd say no because both want to be proton donors. And so how can an acid, a strong acid, attack formic acid because they're both proton donors? You know, they're going to, oh, you take the proton. No, you take the proton. No, you take the proton. I insist. You know, does that make any sense? No, it doesn't make sense. An acid would react with an acid, right? And so the point is that we have to look at it deeper. That is, we have to look at it structurally. This is why Lewis acid-base reactions, like a Lewis acid-base reaction, you got to draw out the Lewis structure, right? And then you got to look at it atom by atom. So we have this, this is just the formula for this, but no, we got to look at this structurally. We got to look at it atom by atom, and then we'll see that chromium is indeed very positive. That's +6. This is going to be a powerful oxidizer. Yeah, so chromate is going to draw electrons to itself. And so this is the whole business about, what we were talking about a long time ago, which is, we want to understand the properties based on composition, but not just on composition, because composition only tells you part of the story. Composition and structure. Good. That's what a lot of people spend a lot of time researching, the properties, structure, and composition of matter. So anyway, the oxidizers here, something like dichromate, but we wouldn't have dichromate alone. We'd also need what? We'd also need, dichromate requires what? Acid. Right, dichromate requires acid. How much acid do you think you need? In this case, 8. How did I come up with 8?
The negative of O2 is 3 minus and 4.
4 oxygens. 4 oxygens, 8 hydrogens will make 4 waters. That's if chromium goes to chromium, and it does. I mean, you could look at it up on the chart too, if that's what we'd need, right? But what's going to feed the electrons to dichromate? Dichromate wants electrons. It's a powerful oxidizer, right? Or chromate, I'm sorry. Chromate wants electrons. It's a powerful oxidizer. So we need something to feed the electrons to it. What is going to feed the electrons to this? The reducer. But do we want the reducer to react directly? No, the reducer is going to be at the other side here. And so pick a reducer that we want to use. Now, does the reducer have to be a reactive electrode? No. The reducer, pick a reducer that's, like for example, can a cation be a reducer? Is that possible? A cation. It is possible. Can you name a cation that would lose electrons? You could look at the chart. Fe2 plus? Fe2 plus could go to Fe3 plus and lose an electron. What else? Copper 1 goes to copper 2. What else? Well, not on that chart, but on the chart in your book is tin 2. Tin 2 is an excellent reducer. Tin 2 goes to tin 4. Since Fe2 plus is over here, let's just do Fe2 plus. So we put in Fe2 plus here. But, so the electrons travel this way, right? But who's, or what is Fe2 plus going to give the electrons to? Yeah, but how do the electrons just hop over there? Now the electrons are going to pass through the wire, the external circuit, right? And so what should we do here? Should we just dip the wire inside this Fe2 plus solution? This is probably FeSO4 is usually what we have. Iron 2 sulfate. Do we dip the wire?
No.
Well, if we could try to dip the wire in here. If we dip the wire in here, the wire is made out of copper. Would the copper react with the iron 2?
Yes.
Well, we can look at it. The way you... I'm using...
What's copper? It's copper.
Well, maybe I should show it on here. Or show it on here.
Yeah.
Takes so long. How do you know? Well, you know, that chart's backwards from the chart in our book. The chart in our book has what at the top? Fluorine at the top left, right? And at the bottom right is lithium. And so this is the way we use the chart. We look for iron 2. Where is iron 2 in relation to everything? So this chart is different. The iron 2 occurs in 2 spots. It's right over here. Iron 2 is kind of weak on the weak end because here's fluorine. And then we look for copper 2. Copper 2 is a bit stronger. So we got copper 2 plus 2 electrons goes to copper metal. And we have iron 2 plus 1 electron goes to, or 2 electrons goes to iron solid. But we also have iron 3. Where's iron 3 located on this? Yeah, if you look at copper 2, iron 3 is actually stronger. Well, we don't have iron 3. We only have iron 2. The reason I'm writing iron 3 here is because iron 2 is on the other side. And so this is what we have here. If I wanted to see, will copper 2 oxidize iron 2? No. Copper 2, if copper 2 oxidized iron 2, it'd form iron 3, which is a stronger oxidizer. And so what we say is copper 2 can oxidize everything below copper, in this case. In that chart, you would say copper 2 can oxidize everything above copper metal. And so the way to rephrase that so you're never wrong, because if you say it oxidizes everything below, then you're wrong half the time, right? Because of this other chart. And so what we say is that copper 2 will oxidize any reducing agent stronger than copper. And so copper 2 is incapable of oxidizing iron 2 because it's a weaker reducing agent than copper. And so we could use these charts to quickly determine everything that copper 2 will oxidize. What is everything copper 2 will oxidize? Copper 2 oxidizes everything here. All these it will react with. And so, as a matter of fact, we can use copper here. Copper, we could dip the wire in here and that would work. But rather than dipping the wire, what we would usually do is we attach the wire to a electrode. Can we make an electrode out of iron 2 plus? Can we make an electrode out of iron 2 plus cations? No. And so we got to make an electrode out of something like this. But hey, why don't I just make the electrode out of iron? If I made the electrode out of iron, is that okay? Well, it depends on what you want your reducing agent to be. What's a better reducing agent, iron metal or iron 2 plus? Which one is more electron rich, iron metal or iron 2 plus? Iron metal. And so if you want iron metal to be your reducing agent, then we make this out of iron. If I want iron 2 plus to be the reducing agent, then I have to make this an inert electrode. Does that make sense? And so let's say I want my reducing agent to be iron 2 plus. And so I get this, iron 2 plus goes to iron 3 plus an electron. This is the reaction that I want. If I want this reaction, then iron 2 plus has to be the best reducing agent in this mixture. If there's something better, then that's what's going to be the reducing agent. That's what's going to be oxidized. And so what I need to do is I need to use an inert anode. And so I have to figure out what is inert to iron 2 plus. What is inert to iron 2 plus? So let's try what, did you just catch what I just said about how to quickly determine? This, okay, let's try a practice one then. Is this clear now? All right, let's take a look. Do you know what this chart is called? First off. This chart is called standard reduction potentials. And so here we have fluorine's the strongest oxidizer. And so we want to figure out iron 2 plus. We want something that won't react with iron 2 plus. Now iron 2 plus is tricky because iron 2 plus is both a reducer and an oxidizer. And so that makes things much more constrained. So let's take a look at iron 2 plus. All right, iron 2 plus occurs on both sides of the chart because it's both an oxidizer and a reducer. And so let's see if I can find iron 2 plus here. I found it right here and here. All right, when I look at it over here, iron 2 plus is an oxidizer or reducer? It's a reducer. And so iron 2 plus will react with any oxidizer more powerful than Fe3 plus. And so all these oxidizers will not work. And I don't want any of these oxidizers mixed in to this beaker because then I'll get direct reaction, right? All right, well I don't have to worry about those because none of these I'm not gonna bubble chlorine in there or do anything like that. So that should be okay. Then I look down here, here's my iron 2 plus here. Here, iron 2 plus is an oxidizer, right? And so I do not want to mix iron 2 plus with any reducer more powerful than iron. So will a zinc electrode work? No, zinc would fail because if I put zinc in here, I'm going to get direct electron transfer, which I don't want. I want the electrons to go through the wire. Zinc would fail. Aluminum fails. Magnesium, sodium, potassium. All these would fail. How about cadmium? Cadmium would work. The cadmium ions are toxic, so we don't want to use that. Lead would work, but we need sulfate. This is the one in the batteries. This is why you have this kind of strange potential because this is in car batteries. Then we can't make a conductor out of that. Nickel is fine. Tin is fine. Copper is fine. Silver is good. Mercury would work, but mercury is toxic. Gold is good. That's it. Platinum's up here, up even higher. And so we'll do something not so expensive, like graphite. Graphite would be good, wouldn't it? Graphite's not on there, but another electrode like carbon graphite would work. And so what is the purpose of the graphite? We need an electrical conductor, right? The electrode's job is to, conduct. In other words, the electrode's job is to take the electron from iron 2, but it's not the electrode taking the electron. What is actually taking the electron? The chromate. The chromate in H+ is trying to pull electrons off of what? Now over here, I have to put an inert electrode here. So this reaction's got to have 2 inert electrodes, otherwise I'm going to get direct reaction. And so for chromate in H+, then it's a little bit more restrictive. And so let's take a look. Do we have chromate? No, we don't have chromate, but we do have dichromate. And do you guys remember what's the difference between chromate and dichromate? Acidity, pH. Remember that? At 1 pH we have chromate. At another pH we have dichromate. Are they, so basically, if I have chromate and H+, well, that means I have to have quite a bit of acidity, and if I have quite a bit of acidity, then maybe chromate's not the stable form. Maybe what the stable form is dichromate. And so what was that inner conversion? Do you guys remember that? Inner conversion? 2 chromates will go to a dichromate, Cr2O7. Why not Cr2O8? You know, 2 chromates would be Cr2O8. Somebody answer that for me. Because when you link 2 chromates, you don't create an OO bond. OO bonds are called peroxide bonds, and they are unstable. Does anybody know why they're unstable? There's one paragraph in Chem 1A. I think I skipped it because I want to talk about it time, but I'm curious if anybody read it. If anybody knows why peroxide bonds are. It's in the quantum chapter, bonds. When we create a bond like this, it's a mix. You know, you look at the electron density. Concentrated electron density here attracts the 2 nuclei together, right? But there's a mix of attractions and repulsions. And it turns out with these OO bonds, the 2 nuclei get too close to each other and the repulsions grow, weakening the bond because of the size. And so that makes this bond exceptionally weak. This bond is very, very weak. And can be broken by visible light. Like for example, in hydrogen peroxide, you have to store it in a brown bottle. The visible light can't penetrate, because if you store it in a clear bottle and visible light gets in there, it'll break that bond. It's that weak. Meaning it's like 100, low hundreds kilojoules per mole. Maybe. Anyway, so we don't create this kind of bond. What happens is one of these oxygens has to go. And so we create a link like this. This is why there's one less oxygen. But if we have one less oxygen, is that going to be stable? Just some oxygen sitting out there? No. We need to stabilize that oxygen somehow. How can we stabilize that oxygen? With hydrogen. And so that oxygen is actually converted into water. Where do the hydrogens come from? From the acid. So we're going to have 2H plus over here. And so as the acidity grows, this is going to shift to the right, to dichromate. As acidity decreases, it shifts to the left. And so, yeah, this was a good example of an anion that was an oxidizer, but this one is stable in basic conditions, whereas in acidic conditions, we need to have this one, right? How about the oxidizing strength of chromate versus dichromate? Would you expect much of a difference there? It should be the same because both of them have chromium in the +6, right? What kind of reaction is this here? Talked about this earlier. What kind of reaction is this? Yeah, a lot of people think this is a redox reaction, but it's not. Because the oxidation states don't change. And so let's go to dichromate. Dichromate's a powerful oxidizer, right? And so dichromate will react with any reducer stronger than chromium 3+. So all these. So for example, if I wanted to use a silver electrode, okay? No. Yeah, iron 2+, copper, no. None of these electrodes, so I have to go gold. I've got to go gold or platinum. Everything else, copper is going to fail. And so I'm going to make this electrode out of gold. Okay, and this would be an inert cathode. All right, now what's going to happen is the dichromate is going to pull, right? It's going to pull electrons. But actually, let's do this under standard conditions. If I do this under standard conditions, what am I going to have? You know, the reason I want to do it under standard conditions is because as we change the conditions, you know, the driving force will change. If I change the concentrations, the driving force, delta G, changes, right? And so I want to do this under standard conditions at 298 Kelvin. And so if I do this under standard conditions at 298 Kelvin, what do I have then? What do I need for standard conditions? 1 mole or 1 molar? 1 molar, everything. What's the dichromate concentration? What's the H plus concentration? If this is 1 molar, shouldn't that be 8 molar? If this is 1 molar, this should be 8 molar based on stoichiometry. Yes or no? No. Oh, how can this be 1 molar and this be 1 molar at the same time? Easy. You know, you sprinkle some sodium dichromate in here to make a 1 molar solution, and then you pour some HCl in here to make a 1 molar solution, so you get 1 molar dichromate and 1 molar H plus. But the thing is, what's going to be the excess reagent? If this were 1 molar and this is 1 molar, then the excess reagent is going to be dichromate because we need 8 molar H plus to make it stoichiometric. But it doesn't matter because this ratio is just, you know, they're going to react in a 1:8 ratio. I could have any concentration I want, right? That's the whole thing behind the ICE table. You know, no matter what the coefficients are, you can have any concentration you want or any pressure you want because it's just going to react in that ratio. And there could be limiting reagent and excess reagent, so it's no problem. This is easy. This could be 1 molar, 1 molar. You know, because you said FeSO4, put that in. So if these are both 1 molar, then what we set up here is a tug of war. Do you see the tug of war? Here are your electrons. And so there's a tug of war for electrons between what and what? Between dichromate and iron 2 plus. So there's a tug of war for electrons. It could go either way, but you already know who's going to win. Who's going to win? Dichromate's going to win. But it won't win for very long because we'll get 0 volts here. Why? This is going to produce 0 volts because it's not because of the hydrogen. We're going to produce 0 volts here because of, actually, I need to change the number of hydrogens here. I'm sorry, it wasn't 8. You know, dichromate, it depends on what dichromate goes to. If you look over here, dichromate ends up as chromium 3 plus. So I got 7 oxygens. I'm going to need 14 H pluses. Sorry. We have to change that. This is going to be 14 H plus. Uh-huh.
When all the atoms do oxidate?
No, we'll see. We'll see. You know, the Fe2, who's going to win the tug of war for electrons is dichromate. So electrons are going to be cold, right? But, you know, there's going to be some resistance here. But what we can do is we can throw a voltmeter on here and measure the voltage. Let me tell you, that's going to be right now. Under standard conditions. So if I hook up a voltmeter on here, I'm going to get 0.56 volts. That's how much voltage I'm going to get. 0.56 volts if I did what? I'm missing something here. Right now I'm getting 0 volts. To get that 0.56 volts, I need a salt bridge. So what should I use for my salt bridge? Sodium chloride? Yeah, sodium chloride's okay in this reaction. If I use sodium chloride, AQ, it's inert. And so what goes over to the anode? The chlorides go to the anode and the sodiums go to the cathode. So that works. You gotta watch out because you don't want, iron 2 won't react with chloride nor with sulfate. Sodium ions aren't gonna react with either of these, so we're okay. So that's inert. Now we'll get 0.56 volts. Now, what we want to do is we want to break it down. There are actually two half reactions here. Iron 2 loses an electron to form iron 3. Dichromate plus 14H pluses gains how many electrons? 6 electrons. To form chromium 3 plus 21 water, right? Oh, They got 21 waters because they added 14 hydroniums. So 14 minus 21 would be 7. Should be 7 waters. Just to a liquid. All right, so basically what we have is this tug of war. It's being pulled by 0.56 volts. The electrons are being pulled this way by 0.56 volts. Now, what we're going to do is we're going to try to break it down. How strong is dichromate? How strong is dichromate? You know, if there's a tug of war and one team beats the other, you say that team is stronger, right? But what we want to know is, we don't want to know that team's stronger. We want to know the absolute strength of that team, right? In other words, we want to know how strong is dichromate. Is dichromate 0.56 volts strong? No. I would say dichromate is more than 0.56 or less than 0.56 volts. It's got to be more than 0.56 volts because there's going to be some resistance. What's that resistance? The resistance is, it has, you know, the Fe2 plus is pulling, plus not only that, not only is the Fe2 plus pulling, it's plucking an electron off the Fe2 plus. You know, taking an electron off the Fe2 plus, does that involve work or no work at all? That involves work. Do you guys remember I1, I2, I3? Plucking an electron off Fe2 plus would be like an I3, right? What is I3? Ionization energy, 3. And the ionization energies, remember, they doubled approximately. And so that's significant energy right there in kilojoules per mole. And so I would have to say that dichromate's, it's got to be pulling with more than 0.56 volts. Now what I want to know is how many volts is dichromate pulling? Is it pulling 1 volt? And Fe2 plus is resisting by minus 0.46 volts. Now this is pulling 1 volt this way. This is pulling 0.46 volts the backwards way, which would be negative on the voltmeter, right? Would you say that's fair? Or would you say that maybe dichromate pulling by 2 volts and Fe2 plus is pulling by 1.44 volts? In other words, I want to know, you know, the individual strengths of each team rather than, you know, the net result. The net result is dichromate wins, but I want to know how strong each individual is so that I can match them up with other individuals to see who will win and by how much. But there's a problem. You've seen this problem before, have you not? What is the problem here that we're faced with? We're faced with 2 unknowns. What are the 2 unknowns? Well, the 2 unknowns is this. We have, we call this E for electromotive force or voltage. This is the voltage. We call this the cell voltage or the reaction voltage. It's under standard conditions. So this is standard cell voltage and standard reaction voltage. The standard cell voltage and the standard reaction voltage is 0.56 volts. That comes from, this comes from the voltage, that is, you know, how much is this pulling? And so this comes from the cathode and the voltage or the potential from the anode. Electromotive force, we call these potentials, sorry. Also voltage, potential, they're all the same. In other words, we need the, for the cathode, how strong is this dichromate plus 14H plus, and then from the anode, it's the iron 2 plus, you know, going to, and so what we see is the net result, but what I want is the individual. We have 2 unknowns. Yeah, we can look there, but that, that's why I'm doing this, because you know what a lot of people don't know what these numbers mean at all. So, you've seen this kind of problem before where we have two unknowns and one equation that we can't solve because we don't have a second equation. Do you remember this problem? Where did we see this before? Two unknowns, one equation. We saw it recently. The last chapter, I'm sorry? Yeah, not coupled reactions, but it involved reaction. We just saw it last semester, but I phrased it in a different way. You know, if I phrase it in a different way, it sounds like something totally different, right? Two unknowns, one equation, but you've seen it before. Can you make the connection?
When we're solving for temperature, using something that's defined in temperature.
Well, yeah, but we got around that. We got around that by making an assumption that, delta H and delta S of 298 are the same. There's something even before that.
Simultaneous.
Not simultaneous. Simultaneous we can solve because simultaneous we have enough equations we can solve for it. This is we cannot solve this. We cannot solve this. And so a lot of people will say, there's not enough information, just give up. Because you can't solve it. Just give up.
We saw it when we were trying to find the percent natural abundance between two isotopes.
The percent natural abundance we can get experimentally. And there we have enough. We get two equations, two unknowns, or three equations, one. Something like that. We can solve it, percent natural abundance. There's something else we could not solve. Absolutely could not solve mathematically. At the beginning of chapter 19, also in chapter 7, the thermo chapter. Yeah, there's something related to that. What was it? It was in Chem 1A, you had this two unknown, one equation, impossible to solve, delta H of formation problem. What was it? They spent a page talking about it in Chem 1A, and then I repeated it in Chem 1B because, it's easy to forget. And I just repeated it last chapter. Two unknowns, impossible to solve. Most people just give up. We did something. Yeah, a lot of people say, oh, that's impossible to solve, This is impossible to solve because I don't know what the voltage is for the cathode. I don't know what the voltage is for the anode, right? And so this is impossible to solve, right? But we do, it's impossible to solve mathematically, but there's a trick that we did. It's just,
You said the E reaction equal to 0 and so forth.
either reaction is not equal to 0.
Like,
Either reaction is equal to 0.56 volts.
So you made one of the anode of half.
Yes, that's how we solved it. So we just say, okay, pick one of these and call it 0, and then give it to the other one. So which one do you want to pick and call 0? Well, it doesn't matter, right? We could just pick one of these and call it 0. If we pick one of these and call it 0, is that right? Can you do that? You can do it because you can never have a cathode without an anode. We saw before with delta H of formation for ions, right? You can never have a cation without an anion. So the systematic error cancels out, and therefore we're allowed to do this. And still it makes mathematical sense because we just arbitrarily choose one as 0. And that solves our problem. Which one do you want to pick? Let's pick this one as 0, and then that says the voltage is 0.56 volts. But that means, this is an underestimate of this voltage, and this is an overestimate, and then but we don't have to worry because they're going to cancel each other out and give us the right answer. So we've seen this troubling thing before, but we worked around it by assuming 1 was 0. And so now you have to keep that, you have to log that in your memory. Iron 2 plus is 0. Iron 2 plus is 0. You have to memorize that, right? What was the 0 before? H plus was 0. H plus was 0. H plus was 0. So you already memorized H plus is 0. Arbitrary 0, we call it, right? Now you have to memorize a new one. Iron 2 plus is our new arbitrary 0. But do you want to have lots of arbitrary zeros? Don't you want the same thing to be the same? If you're going to pick H plus as your arbitrary 0, we picked H plus as our arbitrary 0 for not only for delta H of formation, we picked H plus as our arbitrary 0 for, you guys got to tell me this. We picked H plus as our arbitrary 0 for delta H of formation, and this is the last chapter. Start reviewing your notes for this test. This is, this is like the multiple choice type question, right? Since most people aren't getting this, I'm definitely going to put it on multiple choice. I thought you guys had it. No, not delta. Well, delta G, yes, of course, but delta G. I shouldn't say yes. There's one more thing I talked about right at the beginning. Delta H of formation, delta G, and not delta S. Not delta S, but close. Do you see why thermal kills a lot of people? Because people, it's hard to remember this kind of stuff, isn't it? And you don't know it, and you're using this table, you're using it totally blind, right? You're just assuming, well, somebody else has it figured out. I'll just use it. It should work until it doesn't. But hopefully that doesn't come, because hopefully you aren't given a problem where it would fail. But as you progress, as you get deeper and deeper in science, you're going to be given problems where you have to know. You can't depend on somebody else. And that's the thing. You know, what a lot of schools ask for in the letters is they ask for how independent are they? Are they the dependent type, or are they the independent type person? You know? And so this is why, I was thinking all our labs are totally, you can't tell the difference, because all our labs do this. It's like a cookbook. You don't have to have any skill to do it. You just follow the cookbook directions, right? And so that's why, like the titration lab, I did have a written procedure for that, but I didn't want to give it. Because I didn't, it doesn't show anything. Everybody can follow a step-by-step set of instructions. Everybody will get the same results. No differentiation. But you can expect more of that as you go along. And so, anyway, there's only one more thing. All this was in the context of Appendix D, because I wanted to talk about Appendix D. And so what's the last thing in Appendix D? S, absolute entropy. It's not delta S, it's S. What is the absolute entropy of H plus 1 molar? What is the absolute entropy of H plus 1 molar? Would you say it's 0? No way it's 0, but it is arbitrarily defined as 0. So if somebody asked you, is the entropy of H plus 0, what would you tell them? You'd tell them no, but it's arbitrarily defined as 0. Because you can't separate, you have the two unknown problem. You have two unknowns when one, equation, and you can't separate the two to solve for one. Well, you could, you could do some theoretical calculations, and people have, you do some theoretical calculations, but the theoretical calculations can be quite difficult, and not so accurate. And so this seems like a good, easy way to get around that. And so, of course, people want to do it theoretically, right? And people are looking into it theoretically to get better values for this kind of stuff. But anyway, let's go back to this. So rather than picking iron 2+, what would make the most sense to pick as our arbitrary 0? If we're going to pick something as an arbitrary 0, what do you think would make the most sense? H+. What is the voltage of H+? 0. This is totally arbitrary, right? This is not an absolute 0. Some people treat this as an absolute 0. So they think that, voltage is positive. Voltage is positive. Is the voltage positive? The electrons are moving this way, right? And then they say, oh, now the voltage goes negative. The voltage goes negative, all of a sudden everything should reverse. Is that the case? This is like temperature, Celsius. 0 degrees Celsius is arbitrary 0. So when you're at a positive temperature, everything's running normal. The clocks are going clockwise. But when you go to negative Celsius, do the clocks go counterclockwise now and everything goes backwards? No. So what does the negative mean in Celsius? If you have a temperature of negative 10 degrees C, what does that mean?
Just below the...
Yeah, 10 degrees lower than the arbitrary 0. And so this negative means nothing. The clocks aren't going counterclockwise now. All this negative means is that it's weaker than H+. And so do you see this? These are all oxidizing agents. So all these oxidizers with the positive voltage are stronger than H+. All these oxidizers with a negative voltage are weaker, but are they now reducers because they got a negative? No, they're just weaker than our arbitrary 0. But the arbitrary 0 cancels out when you add the 2. When you add the 2, now a negative means something. A positive voltage, cell voltage, means electrons want to flow left to right. A negative voltage means now the electrons want to flow right to left. And so a cell voltage, a negative, means something because the 0 is absolute. If you have a 0 volts, it means your battery is completely dead. When you have 0 volts here, it doesn't mean it's dead, right? And so this is a key thing you have to understand in using and dealing with electrochemistry. Half cell potentials have an arbitrary 0, whereas cell potentials have an absolute 0. All right, these are called half cell potentials. The cathode, what kind of reaction occurs at the cathode? The oxidation reaction or the reduction reaction? Reduction. And so this is what we call the reduction potential. And at the anode, what do we have? The oxidation potential. And so this is the equation. The book uses a very strange equation. The book's equation, to calculate the cell potential, it says to take the reduction potential and minus the minus of the reduction potential. Why does it say to take the reduction potential and the minus the reduction potential? Well, it says to do this because a minus the reduction potential just flips this backwards to make it a oxidation potential. But, this is just, I don't know. I really don't like that equation because the students should know something. The higher the reduction potential, the more likely it is to be reduced. Right? So that is, the higher the reduction potential, the better the oxidizer. The higher the oxidation potential, now the oxidation potentials, well, these are the reduction potentials. But where are my oxidation potentials? The oxidation potentials, I have to reverse all these reactions. When I reverse all these reactions, the oxidation potential, all we do is to change the sign. And so we don't need two tables. And so if I'm looking at the oxidation potential of fluoride, it's negative 2.87. Negative 2.87, is that a high oxidation potential or a low oxidation potential? Very low. It's the lowest. The oxidation potential for fluoride is the lowest at negative 2.87. What has the highest oxidation potential? Lithium metal has the highest oxidation potential at plus 3.045 volts. And so the higher the oxidation potential, the more likely it is to be oxidized, right? The higher the reduction potential, the more likely it is to be reduced. And so all I do when I calculate the cell potential is I add up the reduction potential. If the reduction potential is high, then that's a pretty big driving force, right? If the oxidation potential is high, and so if both of these are high, then the cell potential should be high. And so I'm going to generate a lot of volts. I take a high reduction potential plus a high oxidation potential, generate a lot of volts. What's the maximum number of volts I can generate? Here, the maximum number of volts I can generate using this chart is by combining the highest oxidation potential with the highest reduction potential. And so let's take the highest reduction potential, 2.87, and then let's take the highest oxidation potential, 3.045. So it's going to be almost 6 volts. 6 volts. So 6 volts means you have a very strong reaction. In fact, this reaction you would have to be very careful with because you're taking the most powerful oxidizer on the chart and mixing it with the most powerful reducer. What kind of violent reaction do you think you're going to see? Yeah, you're going to see an explosion, for sure, with a 6 volt potential. Well, like a AA battery or, those cells, those types of cells, those have 1.5 volts or so. Car batteries have 12 volts. So if a car battery has 12 volts, why doesn't it explode much more violently? Because there's a trick you can do with batteries. A trick you can do with batteries is how you can connect them. If you connect batteries in series, what they call in series, then the voltages add up. So you take a 2 volt plus a 2 volt, that gives you 4 volts. And so in a car battery, they have actually 6 2-volt batteries where the voltages just add up to 12 volts. And so it's only really a 2-volt potential, so it's not really going to be violent. All right, so let's talk about the SHE next. SHE stands for the Standard Hydrogen Electrode. The standard hydrogen electrode is just a container like this, and it has H plus in here at 1 molar. Some anion, just call it A minus. And then they use platinum as the inert electrode. Platinum solid. And then they bubble hydrogen gas here on the surface of the platinum. And the H2 gas has got to be at a pressure of 1 bar or 1 atmosphere. This is your standard hydrogen electrode. So let's go ahead and connect this to our other electrode, which we use gold, although we could use platinum too. And we have our dichromate plus 14H plus in here. This is funny because this is under standard conditions. Under standard conditions, we have to have 1 molar, and not only that, we also have to have what at 1 molar? Because the reaction that's occurring here is dichromate plus 14H plus 6 electrons yields chromium 3 plus 7 H2Os liquid. So if we do this under standard conditions, not only do we have to have dichromate and H plus at 1 molar, but we also have to have chromium 3 plus. It seems ridiculous to add chromium 3 plus in here because chromium 3 plus is actually a product, but we need this, otherwise we have to have non-standard tables, right? We're okay here because over here, well, let's see what happens in this case. What's going to happen is what's going to be oxidized at the anode. Well, what's going to be oxidized at the anode is the species with the highest oxidation potential or the species with the highest reduction potential. What will be oxidized at the anode? The species with the highest oxidation potential or the species with the highest reduction potential? Let's see how you... Yes, good. The species with the highest oxidation potential will be oxidized at the anode. What's going to be reduced at the cathode? That should be easy. The species with the highest reduction potential. And so looking at the anode, does platinum have the highest oxidation potential? Actually, platinum is not on this chart, but let's look at gold. What's the oxidation potential of gold? Negative 1.5 volts. Water. You know, water is present, right? What is the oxidation potential for water? Let's see, negative 1.22. Where do you see it? Here? Yeah. This is a negative 1.22. So what has a higher oxidation potential? Gold or water? Water. Water. Does that make sense? And so water should be oxidized before gold. Oh, let's go to H plus. What's the oxidation potential for H plus? Zero? The oxidation potential for H plus? The oxidation potential for H plus is negative infinity. Why? The oxidation potential for H plus is negative infinity because it has no electrons, and you're taking an electron from something that has no electron. Is it possible? No. And so the oxidation potential for H plus is, in other words, do you see H plus? I don't see it. A lot of people see H plus, but this is not an oxidation. This is a reduction. okay, now we have this anion. Well, this has got to be an inert anion, because if it's not an inert anion, we could potentially do what? We could potentially oxidize it. And so let's pick one. Let's say chloride. Is chloride inert enough so it doesn't react? Well, what's the oxidation potential for chloride? Minus 1.36 volts, which means we oxidize water before chloride. You see that? And chloride is about as hard to oxidize as gold. And so chloride's pretty inert, right? Shouldn't cause any trouble, etc. And then we get to hydrogen gas, because hydrogen gas is being bubbled on the platinum electrode. What is the oxidation potential for hydrogen gas? The oxidation potential for hydrogen gas? 0 volts. Now, what has the highest oxidation potential in this mixture? Hydrogen gas at 0 volts. But you got to remember, 0 volts doesn't mean 0, right? It's just an arbitrary 0. So hydrogen is the best reducing agent in the bunch. And so what we're doing is, earlier what we did was we did this exact same thing, except we used different vocabulary, right? We rather than, we looked at what is the strongest reducing agent. Right? Now we're saying the same thing. Instead of saying what is the strongest reducing agent, we say what has the highest oxidation potential, which is the same exact thing. All right, then over here, rather than saying what is the strongest oxidizing agent, we're going to say what it has the highest reduction potential. And so let's take a look at the reduction potential. What is the reduction potential for gold? 1.5 volts? No. Negative 1.5 volts? No. We did this kind of thing before. And so this is why you got to make the connection between what we're doing in Chem 1A versus what we're doing now. We looked at gold. If gold gains an electron, what forms? Gold minus. And so you'd say the reduction potential is extremely small. Off the charts, probably. Small. And so the reduction potential is not there because do you see gold over here? I don't see any gold metal over here. It must be worse than lithium ion. At least lithium has something going for it. It's positive. You don't want an electron more than gold. Right? And so, gold. In other words, you got to go back to what we're doing at the beginning of the semester. If this is confusing, you go back and you look at how we did it at the beginning. We're doing the exact same thing. We're picking the strongest. What are we picking? Oxidizer. All the oxidizers are on the left. Gold is not here. And so I was just trying to trick you. And so over here, then we go on to the next one. Water. What is the oxidation potential for water? Oh, actually, no, I don't want the oxidation potential. I want the reduction potential. What is the reduction potential for water? It's here. You see it? Right here. Minus 8.277. So water so far has the highest. And then we go to dichromate and H+. What is the reduction potential for dichromate and H+? Positive 1.33. So dichromate and H+ is the highest reduction potential. And then we look at chromium 3. Well, chromium 3 versus chromium 6, you already know the answer. Chromium 6 should be better. But we'll look at chromium 3. Do we see chromium 3 here? No. We'd have to look in Appendix D. Chromium 3 is actually in Appendix D. It goes to chromium metal, but you know this one we don't need because chromium with a +6 oxidation state should be a much better oxidizer than chromium with a +3 oxidation state, right? And so this will be the oxidizer. The reducer here is going to be hydrogen gas. And so the reaction over here is hydrogen gas goes to 2H plus 2 electrons. Those 2 electrons get fed over to the cathode and they're consumed here. Although this consumes 6 electrons, this only produces 2 electrons. How can we balance that out? Yeah, for every dichromate we'll need 3 hydrogens. And so the net reaction is going to be 3 hydrogens plus dichromate plus 14H plus gives us 6H plus plus chromium 2 chromium 3 pluses. Let's balance this. Plus 7 H2Os. This is the net reaction. Net reaction, the atoms must balance and the charges must balance. So atoms and charges must balance. So when we do this and we put the salt bridge in here, we're going to generate a voltage. Let me tell you what the voltage is going to be. The voltage is going to be plus, actually you tell me what the voltage is going to be. Plus 1.33 volts. Plus 1.33 volts because dichromate has a reduction potential of 1.33 volts and hydrogen has an oxidation potential of 0 volts. And so we just add up the 2 voltages. And so we get plus 1.33 volts. That works. All right, so we're going to continue with chapter 20 next time.